Our speaker tonight is a longtime member of the club, N5JEF. A lot of you know Jeff. Jeff is a technology specialist for Placer County. He's on that level that he's in the clouds, looking ahead at what's in the future. Some of us are still doing CW or even AM, maybe FM. We may have graduated to FT8, a digital mode or something like that. Well, Jeff is about 2 years down the road on what's going on in the hobby. And it's where we're going to go in some cases. So this is a little peek into the future. It's a multi-part presentation. He's going to get us started, 30,000-foot view tonight, and then we'll pick it up later on in other meetings with a little more of the detail of what's going on. But anyway, this is the topic for Jeff. Again, he is a Placer County guru, very knowledgeable in the area, and works with all the services in the county when it comes to communications. So Jeff.
Thanks, Jim. All right. Well, thank you. I'm kind of excited about this. It's something that I dream about, think about probably excessively. I am a senior analyst with the County of Placer Radio Services Group. My office is about a little over 500 feet from here. And we focus on mission critical public safety and environmental utilities radio systems. We develop and support the P25 trunking system for Sheriff, Auburn PD, Lincoln PD, EMS, Transit, Parks, Public Works. And I'm also responsible for the county-wide SCADA network with telemetry, notifications, and alarms for wastewater, landfills, and freshwater wells around the county. Previous to that, I was over 20 years as a technical and field service manager in scientific instruments, laboratory, industrial, and semiconductor metrology. And I'm also personally involved in emergency management, search and rescue, and personal preparedness. And I'm a science and technology nerd all my life. Can't help it. So I have a pretty good understanding of best practices for highly reliable, mainstream technological solutions, but that's not what this is about. This presentation focuses on a pair of emerging frontier technologies that will be increasingly applicable to our future. Some practical examples of where this tech can be used currently, and the idea of a playground or sandbox or experimental lab for hands-on exploration of these evolving, developing technologies. It is not a comparison of MeshCore and Meshtastic, but rather an exploration of directions these technology platforms might be heading. This is going to be a very fast-paced overview to fit within 30 minutes, and I'll be happy to discuss any of this at the end or personally afterwards or on Discord. My AI assistant created this nice graphic for me, and it shows that we have 3 levels of this presentation. The first level is a foundational, pretty non-theoretical, just to give you the concept of what we're going to talk about. Then we'll move up to a little bit of the technical aspects, and then I want to talk about potential, the future. And then I'll also talk about our group, Sacramento Foothills Mesh Group. I'll try to fit all that into 30 minutes. So what are we talking about? Well, first of all, spread spectrum, particularly the LoRa version of that. LoRa means long range. We'll talk about what that means. It's an RF physical layer for reliable communications that can be well below the noise floor, like 20 dB, like 100 times less than the noise floor. That's probably the outstanding feature of LoRa. Also, we'll talk about mesh networking, an evolving framework combined with LoRa that gives reliable communication that can be off-grid, decentralized, resilient, and very low power. So, why are these interesting? Well, I'm a geek. The radio modulation technology is evolving for increasingly effective and efficient use of spectrum. And I won't read all these, but everybody here knows about the progression from CW to AF to AM to sideband, FM, FSK, PSK, quadrature, AM, orthogonal frequency division multiplexing. It goes on and on. CSS, which chirp spread spectrum that we'll talk about, Gaussian minimum shift keying, on and on, all the way up to the latest, which has to do with involving AI in our modulation. We've seen some codecs recently that are AI driven. The other side of this is the network technology, and similarly, it's evolving for increasingly effective flow of information. We started with point-to-point communications, right? And point to multi-point broadcast, star or centralized networks, And then flat mesh networks, going to hierarchical mesh networks. That's really where we are right now with mesh, is it's essentially flat. And that causes some issues that we'll talk about. And then networks are also moving to adaptive and AI related cognitive mesh networks, where the network actually has intelligence. It knows how to compress and adapt to conditions. That's what's interesting to me. So what is LoRa chirp spread spectrum? The chirp. This is going to be a non-technical explanation. You can think of LoRa, which stands for long range modulation, as a sliding whistle or a chirp, as with bats, dolphins, or whales. They use it because it works. Most radios transmit by staying on one note or frequency, or switching between two notes, like high-low, like frequency shift keying. LoRa transmits by sliding the note. It's a chirp. Imagine running your finger up a piano keyboard from low to high very quickly. This is an up chirp. The symbol, which is the data bit. Each bit of data is encoded by where in that slide, starting where it starts, the chirp starts. It might start at the bottom, might start in the middle, might start at the top. That's the encoding that gives the intelligence, the data, to the up chirp. The spread is how wide the chirp is. Why it's magic. Imagine you're at a loud party with a high noise floor, to be technical about it. The AM/FM radio analogy is that you're trying to talk by whispering at a constant pitch, blah, 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 blah. If someone shouts at that pitch, you are drowned out. So you talk louder, the room gets louder, nobody can hear anybody. With LoRa, it's different. You aren't whispering, you're sliding your voice from a deep bass up to a high squeak over and over again. And that pattern is cutting through the noise. This allows LoRa to be heard even when the signal is weaker than the background noise. I hope that kind of makes sense as an analogy. And then you have a speed knob. It's called the spreading factor. Basically, how far you're going to spread your slide whistle. We have a picture here at the bottom, an image, which shows the LoRa waveform. On the left, we have what's called the preamble. It's a series of up chirps, 1, 2, 3, 4, 5, 6 up chirps, followed by 2 down chirps. That marks the preamble, the start of a transmission. It allows for synchronization and identification of the transmission. After that, you can see some data, the payload, some data chirps. And you can see that these, on the right, they're starting at different points in the chirp. And that's the encoding of the data. So, LoRa advantages: extreme sensitivity. It can decode signals 20 dB. That's 100 times lower than the noise floor. The ham equivalent is like CW, Morse code, with a filter so tight that it hears a whisper in a hurricane. In the same ballpark as Whisper, by the way, and the Joe Taylor, the JT suite software, JS8, and so on, that are down in the low 20s below the noise floor. But LoRa does not depend on the ultra-tight time, the filtering and the timing that we need with Whisper. You know, there you have to have GPS lock timing. You need to wait 15 seconds for a symbol to come through, maybe a couple minutes to get a call sign through. LoRa is different. Why? It uses processing gain, which is is a characteristic of spread spectrum. We trade bandwidth and time to buy sensitivity. This can give you a link budget of around 150 dB, it should be dBm, with only milliwatts of power. And just for comparison, if you compare that with 1200 bits per second AFSK, audio frequency shift keying, as used by APRS, LoRa would provide about 15 dB better sensitivity and about 5.6 times the range if it was on the same frequency and power. So aside from sensitivity, LoRa has the advantage of multipath immunity. Multipath is where you're in a city or a canyon and radio waves are bouncing off of objects, buildings, and so on, and arriving back at the receiver at different times out of phase. And this can confuse standard frequency shift keying or FM receivers. You get what's called picket fencing. We all know what that sounds like, right, on FM. But because LoRa is a chirp, a moving frequency, a reflection arrives at the wrong time,
for a specific microsecond, and the receiver easily ignores that echo because it doesn't match the pattern. And so it has high immunity to multipath. Doppler resistance, almost the same idea. A moving object, like a satellite, shifts the frequency. And for narrowband modes, this requires some kind of AFC, automatic frequency control. The LoRa fix, a Doppler shift, just makes the chirp look slightly shifted in time. It's the same pattern. It doesn't get confused. The receiver sees the same pattern, it automatically adjusts in the correlator, and it introduces a tiny timing error, but does not corrupt the data. The next one's pretty obvious to us hams. LoRa is a constant envelope modulation. You can use a Class C amplifier, which is very efficient. So, LoRa platforms and use cases. So, LoRa became a product available to the mass market when Semtech started device production back in around 2014. And they started making these LoRa chips available. Right after that, the LoRa Alliance and LoRaWAN, which is a protocol for gateways that can multiplex and coordinate multiple LoRa devices to a central server, basically. That came online right about 2015. It's a star topology, kind of a centralized topology. And this was the basis for all these smart utilities meters that you see, PG&E, water, electric, as well as lighting systems, farming automation, facilities automation, asset tracking, industrial IoT, Internet of Things. So LoRaWAN has millions of LoRa devices around the world, all part of their networks. A point of interest here, LoRa was used for APRS by amateurs in Europe back in 2018, gaining that sensitivity increase. I think it was done in UHF because of the wide bandwidth that would be required. You couldn't really do it on VHF. Helium Network came online in 2019, and it's a way of, it was kind of an add-on to LoRaWAN, I believe, and it was a way of doing that last mile mesh networking of the LoRa signals. They were trying to make money at it. I think they went out of business. Maybe somebody could correct me on that. No, they're still going? Okay. And then there's Reticulum, which is a kind of an offshoot. It's a project that was developed to provide inherent end-to-end security and authentication on any kind of a medium, internet, but also on LoRa networks. So it's of interest. Then there's Amazon Sidewalk, which was introduced around 2020. We kind of know about that as it's on people's front porches, right? And the neighborhoods, or houses are all talking to each other. Maybe more than you actually know. So that's a big one. That uses a hybrid mesh. And then what we're really going to talk more about today is the non-commercial, the smaller groups of individuals and groups who are using Meshtastic or Meshcore. Meshtastic came along in 2020 as the first popular hobbyist LoRa offering platform. And it became very popular. There are probably about 50, I can't tell you right now, I'll look at my chart. But a large number of people are using Meshtastic, and became very popular among hobbyists. And then 5 years later, Meshcore came along, saw an opportunity to redo some of the design decisions that Meshtastic had adopted that kind of painted themselves into a corner. And so Meshcore tries to improve on Meshtastic, but it's comparable. It's the same kind of product. Let's look at, on the right-hand column here, we have Meshtastic and Meshcore applications. I've got a typo here. It says 2000 plus. It really should have been 2020 plus. And we have the preparedness community, off-grid communications. We have outdoors, hikers, skiers, paragliders, privacy activists, journalists who might be in hostile territory and want to have confidential off-grid communication. Hobbyists for radio, drones, robotics, use LoRa for communication between their devices and between themselves. Festivals like Burning Man, they coordinate medical, water, and security. Quartzsite, somebody told me that there were about 200 mesh nodes at Quartzsite recently. Tracking of animals and vehicles, smart farms with sensors. Search and rescue, incident command post, ICP, shelter management, situational awareness. Here's where LoRa can quickly go in and set up an ad hoc, impromptu, small network, providing communication. You can carry a device like this in your pocket and be instantly in contact with everybody in your group through your phone, off-grid. And it has the advantage of being encrypted. So if you need to talk about things that would otherwise be a HIPAA violation, personal identifying information, you can do that because it's encrypted, secure. You can't do that with ham radio. And then the last category here is SCADA telemetry. That's for like our sewers, our water systems, things like that. The backhaul, the last mile, low power sites. If you had a water tank way out in the wilderness that was storing water to prevent against wildfires, if needed, you want to monitor that and see if it's what the water level is, make sure it's good. You could put a LoRa device there. It could run on a battery for 10 years, communicating back several kilometers back to your home base. So those are good, all applications of LoRa technology. Here's some numbers. I won't go through all of them, but I'll point out that commercial LoRaWAN, we estimate about 55 million in Europe, about 40 million in the US. Europe tends to lead in these areas because it's more dense, and so these mesh networks work a little better. The cities are closer together. If we look at the bottom, Meshtastic and MeshCore, we're looking at about 50,000 in Europe and about 40,000 in the US. So about roughly 90,000 of these users. Hardware. What does it take to get started? You can typically get started for about $50 to $100. I got some devices over on the table here that you can look at. But the actual devices themselves, the one I pulled out of my pocket is a $50 device. You can buy smaller devices for 20 bucks, get you started. A lot of times you need two. You need one for your personal node and one on top of your house to get you out as a repeater. RF output for these, it comes in two classes usually. The standard class is 22 dB, dBm. I should have said dBm here. Which is about 160 milliwatts, very low power. Or the higher level is 30 dBm, about 1 watt. Well, it is 1 watt. When you look at these devices, you might be concerned about the noise figure of the receiver. And the standard category is 6 dB noise figure, not great, but standard. And you can get premium devices that are more like 2 dB noise figure, which translate directly to increased sensitivity. You can get standalone devices where you type on a little keyboard, or instead of using your phone, you can get modules to build an assembly. You can get Pi hats mounted on your Raspberry Pi. And there are solar repeaters. You can buy those for about 150 bucks, self-contained box with a solar panel, stick it on a tree, and you have a repeater. Antennas. The antennas can be because this is 900 megahertz, the antennas are small. You can have a whip antenna. I have one on my truck that's 3.5 inches tall, works great. Sleeve dipoles are about so tall. Collinear arrays, there's one on the table over there, 31 inches, 5.8 dBi. Typically antennas are around $15 to $50 for standard omnidirectional antennas. There are directional antennas like panels, Yagis, and corner reflectors, typically a little more expensive, but still 65, 150, maybe a little more for industrial quality. And then you'll find that you might need a cavity filter if you're picking up noise from cellular stations or all the smart meters around you. It's overwhelming your receiver. And if you have a very sensitive receiver for your LoRa device, a cavity filter can be very, very useful. They typically run about 100 bucks. Oops, wrong way. All right, we are at level 2, the engine room. A little bit more technical. I want to mention the effective aperture thing, because we're talking about 900 megahertz. That's 6 times smaller wavelength than 2 meters. And a lot of us are probably familiar with the inverse square law, right? You double the distance, the captured energy goes down by 4. You triple the distance, it goes down by 9, square of the distance. But also you have to consider, and this is not as well known, that at higher frequencies, your aperture is smaller. And so that area is getting smaller and smaller. And so as a comparison, 900 megahertz, a given antenna design will have a 16 dB less energy captured than 2 meters. That's something to think about. You know, you might notice that your 440 radio picks up less energy than 2 meters. This is even more extreme. It's also interesting that the 16 dB that you lose because of the effective aperture change, you kind of make that up, because that's just about the difference you make up in the enhanced sensitivity of LoRa. Not that it matters, but it's just a comparison. Fresnel zone, that's something to think about for these higher frequencies. And here, since you're at 900 megahertz, the Fresnel zone is more collapsed. It's smaller than you would have at 2 meters. 2 meters is basically a 72-meter radius. And if it hits a tree or a hill, it can affect your pattern. The LoRa pattern, a wavefront, may just go right over it. Just one consideration to think about. The 33 centimeter band has some differences in propagation. There's what's called the slot effect, where the wavelength, 33 centimeters, is sufficiently small to pass through doors and windows that 2 meters doesn't pass through. And so 900 megahertz will actually get into buildings better than 2 meters in a lot of situations. You can go down elevator shafts too. I think I kind of repeat that with this urban penetrator thing. On the other hand, the absorption in foliage is much worse at 900 megahertz, especially if the leaves are wet. And just as a standard example, an oak tree in full leaf at that time of year, for the 900 megahertz to pass through, is about 8 dB loss to go through one oak tree full of leaves. Worse if it's wet. So that's where you want to get it up above the trees if you can. The other distinguishing feature about the 33 centimeter band is it's the only band, the only amateur band, this is an amateur band, where the noise floor is primarily determined by legal, unlicensed transmitters. Lots of noise, all these smart meters, everything happening. People call it the garbage band because there's so much noise, so much interference. You could think that's bad, or you could think like I do, hey, that's challenging. How can we work around that? The 33 centimeter band has tiered usage. Primary users are federal government radio location and monitoring services, and ISM, industrial, scientific, and medical. I won't take the time to give examples of all this, but they are primary users, and secondary users must be careful not to interfere or cause any interference with primary users. Secondary users are Part 97 amateur radio operators. And so there are plenty of amateur radio repeaters at 900 megahertz. A lot of those down in LA especially. And then tertiary is these Part 15 unlicensed low power devices that are ubiquitous. And so each level is responsible for not causing harmful interference to the level above it. That's not just a rule, that's a law. Here are a couple of spectrographs, spectrum analyzer photographs that I took back in October. The first one on the left is from my office here in DeWitt. And you can see the picket fence of smart meter interference spread out across the spectrum. You can also see a very large local LoRa peak in between the spikes. The LoRa peak is about 62.5 kilohertz wide. And so it's important that if you want to optimize communication, you want to put your LoRa frequency in between those spikes. But they might depend on your location, your geography, what city you're in. They might vary. The picture on the right is a spectrum analyzer plot taken from up on Sugar Pine Ridge, where you can look down over Auburn, Sacramento Valley, all the way out to the mountains toward the Bay Area. It looks a lot noisier, a lot more complex. It's seeing so much more. And I've highlighted in the upper right-hand call-out, this is the standard mesh core frequency for United States. And you can see it's fairly high in the noise. And so I looked at that, and then I went and said, where's a quiet spot that's not too far away? And I highlighted in the call-out on the lower left the quietest spot I could find nearby. They are 650 kilohertz away from each other. And so this quiet spot, and you see how much lower it is in noise, and this is over a half hour of acquisition. This is repeatedly acquiring it and capturing and storing to make sure it's repeatable. This is the quietest spot I could find here in Auburn. And so I chose that for our Sierra Foothills, sorry, not Sierra Foothills, Sacramento Foothills mesh group as our operating frequency. If we ever decide we want to change back to the US default, maybe we have enough nodes that we're dense enough, we can withstand the noise problem, it's not a big deal to move 650 kilohertz. Our cavity filters will have no problem with that. But for now, we are in a much quieter, like a 10 dB quieter overall area of the spectrum. I'm going to talk about processing gain. I'll try to go through this quickly. The spread spectrum is all about processing gain. It's about spending bandwidth to increase sensitivity. And people might say, well, what about broadcast FM? That's wide bandwidth. We're going to talk about that. But let's start first with FT8, for example, the Joe Taylor technology. There we trade time for sensitivity. Very narrow filter, very long time. Usually it has to be GPS locked for the ultimate sensitivity. And by doing that, you can get down into the 24, 28 dB below the noise. But it's very, very slow. With broadcast FM, we trade bandwidth. We smear the signal wide to make the audio clear, but the cost is that amplitude has to be way above the noise just to work. Otherwise, your FM station is noise. That's not LoRa. LoRa is way below the noise. How does it do it? It trades bandwidth and time to build that pattern, those chirps. And they can be decoded well below the noise floor. Yes? Okay. I'm going to skip over some of that. This drawing is just showing the theoretical relationship between time, bandwidth, power, data rate, and so on. We don't need to get into it right now. Every LoRa radio has what's called a preset, which is 4 things. The frequency, everybody knows what the frequency is here. The bandwidth, everybody has a good idea of bandwidth. It's the width of the chirp and how far it sweeps across the spectrum for each chip in the chirp. A wider bandwidth gives you faster data transfer, but it lets in more noise, reducing your sensitivity. A narrow bandwidth, slower data, but filters out more noise. You get an increase of sensitivity. The spreading factor is how much time you spend sending out every single symbol of data. That's how long is a chirp. And it ranges from spreading factor 7 to spreading factor 12. And going up one step gives you about double the time, takes about double the time, slows it down by double, but it gives you almost 3 dB of sensitivity improvement, 2.5 dB. So that's a trade-off. For our Sierra Foothills, I chose a quiet spot in the spectrum, and I said rather than using spreading factor 7, we're going to use spreading factor 9. Gives us 6 dB better sensitivity compared to the default. Why? Because Sierra Foothills region is the city, the flatlands, the mountains, the foothills. We need that extra spreading sensitivity to cover our varying topography. We are not San Francisco, where everybody's dense, and it doesn't matter much. More on that later. And the last parameter of the 4 in the preset is called the coding rate. This is forward error correction. They add extra bits. For every bit you every 4 bits you send, you'll have some number of redundant bits that they'll do error correction. And a coding rate of 5 means that for every 4 bits you send, 5 bits are actually, for every 4 bits of data, 5 bits are sent. Coding rate 8, for every 4 bits of data, 8 bits are actually sent. So you have 4 data and 4 redundancy. And it's interesting that users can choose in MeshCorp, they can choose what to set their coding rate is. So if you have a weak transmitter or you're in a bad location, you know it's going to be hard for people to hear you, you can personally choose to increase your coding rate, and everybody who hears you will accommodate that without any changes on their end. Okay, that's the technical. Now I want to talk about what does it mean? Where are we going to go? So, my AI friend thought this is all about intelligence. Put the brain in the middle. It's talking about self-healing infrastructure, decentralized mesh, fancy stuff. What kind of knobs and levers do we have to adjust with LoRa? We can adjust our processing gain by changing the bandwidth, changing the spreading factor. And there are possibilities. Right now the mesh is all on a chosen frequency, a chosen single spreading factor, a chosen single bandwidth. But we could consider running different spreading factors on the same mesh, on the same channel. We can get away with that because LoRa has this property called orthogonality. You can actually transmit at the same time, on the same frequency, two different signals, and they won't interfere with each other up until they get about 20 dB. If one gets 20 dB stronger than the other, then you have a problem. That's 100 times stronger. As long as they're within the range of within 20 dB, they coexist. They see each other as slight noise rather than interference. It's an interesting property. It lets you run multiple signals at the same time. You can have a fast signal and a slow signal sharing the same channel at the same time. That's powerful. I mentioned CAD, channel activity detection. This is like the carrier-operated squelch. This is like PL, except it works 20 dB below the noise and fast. So if you wanted to synchronize on a signal that was one of these high-speed spreading factors, you might have it switch over, detect that carrier, and lock on and demodulate the high-speed data, then come back and go back to routine processing. That's an oversimplification, but it gives you some flexibility in more intelligent meshes that we don't use right now. And then the last one here I have is FHSS, that's frequency hopping spread spectrum. This is actually standard by almost all the commercial users. And LoRa, Meshtastic and MeshCore aren't using frequency hopping at this time. It's more complex. Normally it takes a centralized infrastructure. It is possible, in theory, to use that preamble. Remember the preamble I mentioned? You could set up a preamble scheme where you could do frequency hopping and have an assigned listening frequency. The various repeaters could listen, and when they hear that preamble, they could synchronize it on it, and it would tell them what the frequency hopping schedule is going to be. And they could synchronize for frequency hopping. The interesting thing about that, remember the picket fence, all the spikes? In theory, you could frequency hop in between all those spikes, into all the empty spaces in between them, and avoid almost all that noise. And you'd be almost invisible. Low probability of an intercept, in case that's important. That's LoRa, things we could do in the future. Haven't done it yet, most of us. The other side is networks. What can we do there? First point is flat meshes don't scale. MeshCore on Meshtastic ran into that immediately, or when they started to get up in over dozens of nodes, they ran into congestion, and things tend to squash to a halt. Once you get past about 20 to 40% channel utilization, the network fails. MeshCore, starting 5 years later, tried to be a little smarter. They reduced the overhead, but they're still using a flat mesh network, a flat structure. It doesn't scale. Right now, Puget Sound has about 600 nodes, and they're complaining about how their congestion is starting to stop things. LA is already running into that. They're going to shorter and shorter times to try to avoid it. Same thing the Bay Area did already on Meshtastic. So flat meshes don't scale. But there's this thing called the constructal law that I want to refer to. And you're going to think I'm going way off target right now, but just bear with me for a minute. Constructal law says that for a flow system to persist, it must evolve to provide easier access to the currents that flow through it. So I have examples from water flow, vasculature, blood flow, and transportation flow. With water flow, you have the sheets of rain that come down, the drops that come down. They coalesce into rills and gullies, become streams and brooks, become tributaries, became a mainstream river. It's branching to maximize flow. Nature found a way to do that. Vasculature, blood circulation. The aorta, high volume, high pressure. Arteries, smaller aorta is a big artery. The smaller arteries are distribution. They're smaller. The valves that flow handle the smaller flows. And then you have capillaries, tiny flows. Again, branching, layers of flow. Nature found a way. Transportation. We have freeways, interstates, fed by arterials, which are fed by collectors from the city streets, which are fed by local roads, which are fed by driveways. Again, humans found a way to maximize flow in their design. But we're not doing it with a mesh yet. It's all flat. It doesn't work very well. So the point is, we should have top-level, interregional, high flow, maybe high-speed links with traffic filtering. We don't need all the Bay Area traffic coming into the Sacramento area, just the parts that we care about. Then high-level repeaters with a high level of bandwidth from mountaintops and towers, and then mid-level services, lower bandwidth, but having local services like repeaters, room servers, and then low-level connectivity, the rooftop repeaters. It's a layered, branching kind of a layer that manages flow. That's the idea. So first, we have to achieve scaling and efficiency, and then we can move on to resilience and adaptability. What happens when a node disappears? It moves. What if it's a mobile node? We need some resilience. We need some adaptability. These are all pointing in the direction of increasingly intelligent mesh networks, which we don't have. These are the opportunities. This gets me excited. I say here, efficiency creates trees. That's the branching. Resilience creates crosslinks and loops. But then finally, dynamic, intelligent rerouting of flow with changes and growth is a level on top of that. None of this exists right now. I think it's interesting. I'm going to get philosophical here for just a moment. Evolving, developing a common theme. There is a common underlying theme here. Technologies increasing in capability and efficiency. Facilitating structures increasing in depth and breadth. Supporting action and interaction. Increasing in expression of human agency. What matters to us? I think I'll skip that paragraph since we're trying to move on quickly. Let's talk about the Sacramento Foothills Regional Mesh. We're done with the concrete, we're done with the theory, we're done with the philosophical theoretical. Let's talk about Sacramento Foothills. So, back in May or so, those of you on our chat in the club here might have noticed that N5JEF was saying, "Oh, look at this, Meshtastic, it looks like fun, mesh networking on LoRa." And I was posting about it, and I started to get involved. And it was great back in May. And it kept growing, and there started to be congestion. And then, come around August 8th, I think it was, last year, the Bay Area, which was already suffering from massive congestion because of their high-density nodes in Meshtastic, they set up that they had communication going through their Fremont Peak repeater, and then they included Mount Diablo and Mount Vaca, and suddenly, Bay Area traffic was flooding into Sacramento, and we couldn't communicate anymore among ourselves. It really, really hurt. And that went on for a couple months. And then some of the key people in the Bay Area said, well, we're just going to have to go to shorter spreading factors. You know, we can afford it. We're dense. We're a city. We don't need the link budget. And so they increased their speed of their connections, and it kind of fixed it for them. And all the spread out Sacramento nodes suddenly went, we can't even connect anymore. We're going to try to hook up to the Bay Area, and some of them migrated, but it didn't work very well. And so here's a before and after picture. This is at the very end of that tragic period, September. And you can see that my node here in the upper right-hand corner, so this is Sugar Pine, it's connecting pretty well to all the medium, slow nodes. That was the preset we were using at the time. Things are pretty good, actually, once I put that one up there. I could get all over everyone's head over to Vaca, over everyone's head to Diablo. And it was actually working for me being on the edge of the mesh. Other people were still struggling because they're in the middle of the mesh. But then everybody kind of migrated out of Sacramento and joined. They either quit operating in Sacramento, or to the extent that they could, they joined the medium fast, the high speed fast nodes. and so it hollowed out Sacramento. So I switched my node to mesh core. I figured it's time to try something new. And now we have just a few slides to show the development of mesh core since late October of last year. This is the way it looked with coverage back in January. We have Auburn. You can see the yellow highlight in Auburn area. We had 5 nodes there eventually. I started with Sugar Pine, DeWitt, my home, and then we added W6EK and Auburn Folsom. So Auburn's pretty well covered, but Sacramento is still in the high path loss. In about a week or two, we expect to have the Carmichael Elks Tower. You can see that it lit up the Sacramento area with yellow. This is a projection of what we expect to see in a couple weeks. And we're going to have good coverage through Carmichael, Fair Oaks, Citrus Heights, in that area. Following that, we have Berryessa coming online, which is going to fill in Woodland, Davis, and Elk Grove. After that, this is kind of exciting. I understand that AIR, haven't met him yet, is talking about a tower in Georgetown. And a node there would be very interesting in Georgetown because it would hit all the hilltops for miles around. Doesn't have much flatland to illuminate, but it would hit all the hilltops, and from there you could have repeaters, small repeaters, down to people's houses. And so that's exciting. I think I'll leave it at that. We were speculating in the group about going part 97, 10 dB more power, more flexible bandwidth controls, but then we'd have to do ID requirements, no encryption, automatic control restrictions, third-party traffic restrictions. It's kind of difficult, but it's a possibility. We also thought about going part 15, but implementing frequency hopping. I think that's an excellent plan for the future. It's going to take some time. We're also talking about bridging with the Bay Area, Central Valley, Tahoe, and more intelligent network components. This is a picture of the West Coast mesh core community. There's a lot of nodes in Southern California, a couple hundred in the Bay Area, and a small cluster up in Sacramento area to Auburn. If you want to know more, join us on Discord. There's a link here. And open for questions. How are we doing for time, Mark?
We are out. If we have any questions, we have a hand in the back. Please state your name and...
let me know if you have questions.
Yeah, Brian, AI6US. Great technology. What the hell do I do with it?
So, as I mentioned, it has real practical applications for ICP, incident command posts, and manning shelters, that kind of thing. Talk to Dave about that. It has application for various ad hoc, camping, that kind of thing. Other than that, a lot of people really enjoy the social aspects, chatting, and a lot of people who would be, well, 85% of the people in my group right now are all hams. And they like playing with the technology. They like building the nodes, watching it grow, so it's fun. For me, I like geeking out on what could it be in the future.
Don, you had a question?
My name's Dan, KN6WQU. So I have joined the Discord, and I'm kind of confused on how to connect to your guys' N5JEF stuff. So I'm not sure how to do all of that. I know, like, look at the pin network, but I'm not a social media guy, so I don't really.
Yeah, but you're on the Discord already.
Yeah.
Reach out, and I'll connect with you.
Okay.
I will start probably by creating a coverage map for your area and advising you on how to get started.
Okay, we can take maybe one more. Scott in the back.
Mark, we have a question from online as well.
All right.
Scott, KM6RFP. Jeff, is any of this going to reach out in the Lincoln area?
Oh, we have two new nodes in Lincoln just in the last 2 days.
Okay.
Yeah, it's going very quickly.
Great.
There you go. From the net, from the Zoom.
Joe, KD6HLN, would you like to come off mute and ask a question? If not, type it out.
How much data can it handle over what time frame?
I can't understand.
Can you repeat that question? They couldn't understand you. You had trouble over time.
I'm sorry. How much data can it handle over what time frame?
How much data can we handle over what time frame, Jeff?
Yeah, so generally speaking, the communication is at a rate of about 1,000 bits per second, and that includes the overhead. It's for texting. It handles a natural rate of texting. given the density of our mesh. It's not for voice, it's not for anything fast.
All right. Thank you very much.